Hello, everyone. My name is Andrei Alexeyenko. I'm from KTH in Stockholm. And today I'm talking about comparing the performance of SYCL runtimes for molecular dynamics application. So about the title, comparing the performance is self-evident. I will be talking specifically about runtimes, not about compilers. Of course, you can skip the performance of compile of how well the kernels are compiled entirely, but that won't be the focus of my talk. And since most of the molecular dynamics today are run on GPUs, yeah, it will be GPU runtimes, namely OneAPI and SYCL. And why would we want even to care about the runtime performance? If the kernels run well, why bother? Well, as you can see, the GPU performance have been growing quite steadily over the past years. It's a mix of different devices here. So it's both laptop or integrated GPUs and high-end server GPUs, but overall we can see pretty nice growth. So flops are getting cheaper and cheaper. Yet the latency to launch the kernel, it's OpenCL benchmark, but it more or less holds true for even native CUDA, just that we had more data over more vendors for OpenCL. Latency to launch the kernels is not getting significantly less. Sure, the red dots here have some downward trend, meaning that certain vendor is optimizing their runtime, but it's not going much less than 10 or 10 here, maybe like 3 microseconds. And yeah, your kernels get faster, but the fixed overhead to launch the kernel is not getting reduced. It stays the same. And besides, new hardware is coming from all 3 major GPU vendors with truly unified memory. So soon on server hardware, we won't have the need to copy data back and forth. So that source of GPU offload related overhead is also going away. So compute gets cheaper. Probably we won't have to worry about data transfer at all. And the fixed cost to just launch the things on GPU, to synchronize with GPU, all that stuff is not really getting reduced. Besides, heterogeneous systems doesn't only mean that we offload things to GPUs. That means that we also can overlap work on GPU and CPU. And the more time we spend just trying to keep the GPU busy, the less useful work can CPUs do. And that is a big problem that has been shown on for a while for molecular dynamics, but yeah, probably it will affect more applications in the future. Molecular dynamics is kind of like n-body problems, if you're unfamiliar with that. We have a bunch of atoms that interact with each other according to some fancy physical equations, and we just iterate over Newton's equations of motion over and over, and we just need to make a lot of steps to reach any reasonable, to simulate any interesting physical process. And another issue with molecular dynamics is that often the problem size stays the same. If your system of interest has 10,000 atoms, it has 10,000 atoms. Yeah, you're not gonna increase that number and scale and use weak scaling. And GROMACS is one of the molecular dynamics engines. It's quite old open source code. We are trying to keep ourselves modern, use C++17. And we are trying to stay portable, running on a wide range of systems. Basically, we do have students running GROMACS on their MacBooks. we have Gromex as one of the target acceptance applications for Lumi. This number 3 in top 500. So yeah, that's quite a huge range of hardware we want to support. And of course, we need to support more or less all the GPUs. And historically, first we had CUDA for NVIDIA, like I guess many code that adopted GPU early on. Then we had OpenCL as a portability layer, and in 2020 we started shifting to SYCL while deprecating OpenCL because, well, you have seen the program of IWOCL. There is pretty much no talks on OpenCL, no activity going there. So yeah, we decided to follow the crowd, and yeah, since most of the activities is happening in SYCL, probably that's where we should focus our porting effort too. And yeah, as I said, Gromex has quite a bit of history, so it was designed for CUDA, and keeping that in mind, in SYCL, we also inherited some of those design choices, namely it's in-order queues and not DAG-based scheduling, manually managed, manually copied USM-based memory, and more explicit synchronizations. So yeah, something that was added in SYCL 2020 for closer compatibility with CUDA. And yeah, in terms of SYCL frameworks, we support one API to run more or less all GPUs, and HipSYCL for AMD and NVIDIA. We haven't tried HipSYCL on Intel GPUs, although perhaps it will work. So that's the stage. That's what we are comparing. And if we look at purely kernel performance, here is a bunch of kernels. We are comparing to our pretty well optimized native CUDA. And I would say it is very good. We haven't ported all the hardware-specific optimizations from CUDA to SYCL, in part because NVIDIA was not our primary target for SYCL. We have CUDA, so SYCL we use primarily for AMD and Intel devices, but also because yeah, at this point already some optimizations that benefit NVIDIA devices start hurting AMD and vice versa. So you either have to duplicate the code or have some really complicated and poorly maintainable metaprogramming things. So overall, most kernels are within 10 to 20% slower. Some are even faster than well-optimized native NVIDIA code, native CUDA code. That's pretty impressive. So that is a huge success, I would say. These kernels FV are run quite rarely, so they're 50% slower. That doesn't really matter all that much. But if we look at total application performance, things are not looking that great. So if we are running large systems with many atoms and with very large kernels, yeah, we get within 10% of native, again, for portable, really portable code. That's a huge success. For smaller systems on powerful GPU, we get 2 times lower performance. And yeah, that's market dynamics, but I believe that might be relevant for any code that has to deal with launching a lot of small kernels. So let's look what happens here at this inflection point. If we look at our typical GPU schedule, that's what's happening. On CPU, we are launching a lot of GPU work. And then we are, after launching 10 steps, 10 packs of kernels, so to say, we are waiting for them to complete. And at the time, GPU is crunching the numbers as it should. That's what typical step bunch of work does. So we have several streams, pretty nice overlap between different kernels, all as well. And if we look just at the length of GPU workload, it's more or less the same here for native CUDA, for HipSYCL, for one API. So yeah, once things are scheduled on GPU, we get nice overlap, we get 10% performance difference as expected, everything is fine. But for example, for HipSYCL, if we look at the traits, we can notice that we start submitting things here, and they only start executing later. Here, the gap is even longer. That is related to a feature in HipSYCL that, in many cases, is supposed to improve performance by allowing us to overlap and actually build a DAG and schedule things more efficiently. But if you already schedule things manually, that just adds this overhead, resulting in lower performance. Luckily, Axel was very receptive to our feedback, and there is some magic environment variables allowing us to disable this caching behavior. So we have almost immediate execution. So that is the major reason for this slowdown on HipSYCL. And for one API, the plot looks somewhat similar, but the reason is quite different. If we look at, now let's look at the CPU side of things. Things are launching for one API really close, but if on CUDA launching a kernel takes around 10 microseconds, on one API, unfortunately, we have to do a bunch of additional work to create, destroy an event to synchronize things that, in CUDA, we know that we don't need to, for example, here, create a new event. We just need to insert a synchronization here. Unfortunately, we cannot, in standard compliant way, signal it to the runtime. So runtime has to do all this busy work. And this submission takes 4 times longer. And if we compare the traces, here we have submission, then just waiting for the GPU to do its work. Here, CPU is entirely busy all the time, just submitting, just keeping the GPU busy. And if we go to the left of our size plot, if we look at the smaller systems, obviously kernels get even faster, but the CPU time stays constant. So we are hitting a wall. We cannot really run any faster. So that's why we have this hockey stick shaped drop in relative performance. Because CUDA, native CUDA can still schedule things, but one API hits the CPU limit. And with HipSYCL, we get pretty huge performance improvements here. We lower this, we move this wall to the left by disabling the runtime caching, which is really nice to have, and really nice feature to be aware of if you are also dealing with similar cases. And what about AMD? One would expect things to be more or less similar because it's heap is also very similarly organized to CUDA. Backends for CUDA and heap in one API and HipSYCL are quite similar. And performance is a bit more random, but also not too bad. 50% slower for some kernels, 20% faster for other. And again, it's native heap port made with help from AMD people, well, made by AMD people. So the fact that in some cases, SYCL noticeably outperforms heap is impressive. Yeah, sometimes, yeah, there are some kernels that are 2 times slower. Most likely it's some kind of compiler inefficiency, maybe some carefully placed pragma role will fix things. We just haven't had time to fully dig into it, and it's not the most time-consuming kernel. So, yeah. And again, here we more or less guess, have a good idea why things are slower. It's just that porting some optimizations is hard in a actually maintainable, sustainable manner. And here, if we look at the total performance, again, we see that things are really good at right side when it's most just having GPU crunch numbers fast enough, and lower left side when we have small systems and when we depend on GPU runtime, on the runtime, just keeping GPU fed, it's not as good, but things turn out to be a bit different. So yeah, if we look at, again, typical GPU step, we notice that there is, while kernels are not that significantly different, most of the time spent either here or maybe here, spread, gather, non-bonded F. The times just to do the GPU work are quite different between all the implementations. And interestingly, disabling caching actually makes things slower on the GPU side. So yeah, and if we look on CPU side, we notice that there is this huge nasty heap stream wait event, which is an API call to the underlying heap runtime, and are even visually much wider than most of the other API calls. And yeah, if we plot the time for this API call, we see that it behaves very differently depending on how exactly you're scheduling things. If you're running heap native and you're able to submit things to runtime very, very fast, you actually start hitting apparently some internal barrier or synchronization in the heap runtime itself. So you have this very long 35 microseconds API calls just to insert the barrier on GPU. They're not waiting for anything on the CPU. They're just submitting a barrier between one GPU task and the other. Yeah, SYCL is submitting things also in batches, but slightly probably less intensive, so it's not as bad, but similar. If we disable caching and submit things as soon as possible, yeah, we get some overheads, things are more spread out, so runtime is not as tired. And with one API, in a way, these events that are painful on CUDA, in this sense, they improve things because we don't submit that many GPU tasks per second. So the ROCm runtime is not as overwhelmed. So the median time stays the same, and this is lower. Yeah, it's 25. The first quartile, median, and third quartile. So it's more distribution. We still get some slow calls, but half at least is well within 2 microseconds. On CUDA, it's all the calls to the respective CUDA API are well under 2 microseconds. So that's not really a SYCL problem, but it's something that users of SYCL runtimes should be aware that, yeah, sometimes same operation can take arbitrarily different time on the CPU, depending on kind of random measure of how fast you're submitting things. So yeah, that makes the plots more smooth because this nasty behavior of the runtime actually affect also the heap more than, say, one API. So unlike CUDA, we don't get the hockey stick shaped wall. We just get this slow increase. But otherwise, we still have the very similar issues that as with CUDA, is just that they are additionally confounded by unpredictable runtime behavior. And yeah, also what this runtime behavior makes is that it really introduces delay in the GPU scheduling. So here we have 11 microseconds between two kernels. And here we have 48 microseconds. Again, it's GPU runtime is perfectly capable. It's just that we have this unfortunate heap wait event that takes 17 microseconds. It delays all the further API calls. We have extra API calls to insert event. It all adds up, and yeah, here we get this 50 microseconds of GPU doing just nothing. It just sits there waiting for work. So as an application developer, what can you do about it? For HeapSYCL, there is very nice coarse-grained event extension that allows us to avoid such things. That it's a way when submitting the GPU task to explicitly signal to the runtime that we don't want a synchronization event from that test, so you don't have to insert or create any more events. For one API, there is a similarly spirited extension of discard events, which unfortunately is not suitable for our task because it's not per command group. It's for the entire queue. So if you have several queues and you still want to synchronize with them, you have to, at the moment, accept this cost of all the extra API calls. And additionally, that's not something that can be done in the application, but can be implemented in the runtime, is just reuse the pool of events instead of every time creating a new one. Create event, record, destroy. Create, record, destroy. You could just use the record and slash the number of these API calls in 3. Additionally, as a user, you should be aware that you have some knobs to tune for HeapSYCL. You have the HeapSYCL RTMax cache nodes and HeapSYCL RT scheduler environment variables that influence how your schedule behaves. But yeah, it's not always beneficial to just disable it, because sometimes, as shown with HeapSYCL, if you're just submitting two things too fast, and that was plot for single GPU, it gets worse when you have multiple GPUs in the system. So sometimes you might want to set it not to 0 or 1, but to some intermediate value. So you still have some lag between submission and execution, but you still submit them somewhat in batches. So yeah, it might require tuning for specific hardware, for specific way you're submitting your work. And long term, well, hopefully we'll learn a bit more later today about work on SYCL graphs, because for multi-dynamics application, for some other codes where we have iterative, repetitive work, instead of just submitting 10 kernels and accepting 10 times overhead, we can perhaps prepare, pre-bake the graph, and submit only one single GPU task. And that is also already possible with CUDA and heap graphs. And there is a lot of work going on SYCL graphs right now. But that has additional problems. But it's fine if you have only full GPU-based runs here. If you have heterogeneous systems and you want to also have CPU tasks in your graph, and you want probably to pin your task to certain cores, so you reuse cache, it gets complicated. But it's really a promising direction that hopefully the whole SYCL standard industry implementations will go. So to conclude, kernel performance, in our opinion, is nowadays not the big problem. It takes time. It's not easy to get within 10% of native, but it's doable in, I would say, performance portable manner. You might have to do some hardware-specific optimizations with if-def and conditional compilation. You might have to spend some time profiling to find out where, for example, loop is not getting unrolled, or where it is getting unrolled and just uses too many registers. So yeah, there are some difference in behavior, but yeah, it's all LLVM in the end. So as long as you convince the compiler front end to interpret your code correctly and see through possible additional layers of syntactic sugar, it's all fine in our opinion. Besides, if things are really bad and some kernel, you just cannot get it to run fine with SYCL, and you really want it to run on this specific hardware as fast as possible, yeah, you can just get it in heap or native CUDA and use interop, and yeah, okay, it's not portable, but if you have some high-profile target and you want it to work on, you can do that. But if you're like us, have to deal with the cases, it's not the only case in microdynamics, but it's one of the cases when you have a fixed, very small problem size and you have to scale things very fast. Well, yeah, this can backfire in many different ways, and you might have to look from for solutions on different runtimes in different places. So yeah, SYCL unfortunately adds some overhead. Both OneAPI and HipSYCL are guilty of that, but yeah, sometimes it's not even SYCL. Sometimes it's just the way ROCm behaves. CUDA is much better in this respect. It's more mature, yeah. But yeah, if you're aware of it, you can partially work around of it, and yeah, either through environment variables or through annotating the code, or through just bugging the runtime developers to fix things for you. That worked for us, and yeah, OneAPI and HipSYCL are quite active on GitHub, and I think quite receptive of feedback. Very good. And yeah, I would like to thank Intel Corporation for and specifically Mark Abraham, Heinrich Bockhurst, and Roland Schultz for their help with initial OneAPI porting and like later optimization. Unfortunately, I wasn't able to add some results on Intel hardware. There's some also interesting things, but yeah, unfortunately less hardware than we would like for thorough testing. I'd like to thank AMD for sharing their heap port, so we had native backend share, Axel for his help with all things HipSYCL, and the rest of the Gromax team. And thank you for listening.
Thank you. Maybe time for one or two quick questions. Yeah. Hi, I'm curious. What are you using for FFT?
QFFT for CUDA, VKFFT for HIP. Even AMD is using it in their HIP port.
And also, if, can I have a second question?
Sure.
I didn't quite get this node caching thing. Like, what is this cached nodes you spoke about with SYCL? I didn't quite get why that was an improvement. I don't know what problem it's solving.
Yeah, so that's this part. So when you submit a new work to GPU, it first gets cached in the runtime in hope that maybe it will be dependent on, it will go to some out of order queues and the runtime can overlap it and run it in parallel with some other work, which in general case should be beneficial, but in our case with already optimized and manually parallelized schedule, just add this launch overhead, which for small kernels really add up. This step gets 2 times longer.
Yeah, I get it.
One more. I thought Axel would have to put his hand up. Go on, Axel.
So I'm curious about this ROCm behavior that you've discovered, where the stream synchronization is worse the faster you go. So my question is AMD aware of this issue, and are you aware of any tuning knobs that you can use to affect the behavior of the ROCm runtime and maybe fix this?
They are aware, and that is with ROCm 5.3.3, and it was much more API calls had this weird behavior in previous versions. So yeah, they are aware, we contacted them, and they're fixing things.
All right, cool, thanks.
Yeah, not sure about the timeline, but yeah. Basically, it was worse, it gets better. Hopefully the trend will continue.
Great, thank you. I think in the interest of time, we'll move on. So let's thank Andre again. Thank you very much.
Yeah.